The title of this talk is Real-Time AI at Scale. My name is Shtub, and I'm Head of Training at ScyllaDB. A few words about myself. A software engineer, that's my background. I'm based in Israel, in Tel Aviv, and I've been with the company for quite a while, almost 8 years. The agenda for my talk today, I'm going to focus on AI and specifically on infrastructure that powers AI, and more specifically, databases that power AI applications. So I'll start with stating the problem, how AI applications or AI in general can break databases, what's different. And then I'll talk about AI at scale architecture, talking about how modern database architecture can solve some of those problems. And after that, I'll dive into some use cases and examples, different AI applications like vector search, like feature store, and talk a bit more about those, also using real-world use cases. There is a question by Auto, hi Auto, and excuse me in advance if I mispronounce names. The question is, will the recording be available? And Omid already answered, so thanks for that. I'll also say that this talk is happening live right now. It's not pre-recorded. My goal is to make it as interactive as possible and also to try to sort of gear it towards the audience, towards you and towards what you want to hear and towards your level. And that's why I added some poll questions so I can sort of gauge your level and adapt my talk according to your level. And I said that earlier, but some people joined afterwards. At the end of my talk, we're going to do a quiz. It's quick, it's interactive, it's using the Slido platform. And you can already scan this QR code and be ready. You can do that even with your phone, just a few seconds. And the winner of the quiz will get a $50 gift card for Amazon or such. So stay tuned for that. It's just, I believe, 4 questions that are quite easy, just to make it a bit more fun and interactive. All right, so I'll start with stating the problem. AI breaks databases. What does that actually mean? So here we have an example from Jason from Replit, and he tweeted about a year ago that he was doing some vibe coding, and then it sort of got out of hand. Happens to the best of us. And the agent deleted their production database. Okay, so that's an example of AI going bad and breaking the database, but that's actually not the focus of my talk today. My focus is about workloads. So AI workloads can create such an impact on the database that it can cause it to break. Okay, so why are AI workloads different from regular workloads? First, AI is used at scale. We're talking about huge amounts of data. And then second of all, we're talking about queries that can be given in enormous bursts, okay? And I'll talk about an example in just a second. But think about a human interaction with a database where me as a user in some application or website, I click on a button, something's happened and I get a response. So that is very expected. It takes me some time to click on the button. I wait a bit, I get a response. That's not really the case with AI and specifically agentic AI. There it can be dozens or even hundreds of agents working in parallel and sending bursts of thousands of queries per second or even more. And that's a whole different story from human interaction with the database. Next, we have low latency expectations. So I'm not sure how different this is from human interaction, but again, because we're talking about a larger scale, with AI, imagine you're even on Google asking a question to Google AI in the search. You would expect an answer quite fast. You do get a message thinking or doing research or whatever, but if it takes more than a few seconds, you would not get a good user experience. And I'll talk a bit more about latency in just a second. Um, Last but not least, we're talking about different kinds of data and also mixed types of data. So think about vector embeddings or vector search or text search and some things that are working together along with complicated mathematical algorithms or operations that are running on the data. That creates a big load. In terms of where we are and where we're going, so I created this small timeline. So this is where we are. We're at the real-time AI age. Probably most of you are already using AI in one way or another. And in the very near future, we're looking at agentic AI. Some people are already using that. And the difference, or the way I see the difference between where we are now and agentic AI is that right now we're getting some assistance from AI. For example, finding a recommendation for a hotel or asking some medical question. In the very near future, instead of asking AI what's the best hotel in Sri Lanka, for example, I could ask AI, for example, this is the type of vacation I want to go on. These are the dates. Take care of it. And then the agentic AI would create a number of agents, find flights, book those flights, find a hotel, book that hotel, maybe some tours, and so on. Okay, so that's where we're at and that's where we're going. This is an example from Next AI, another company, and they faced an outage that is related to database workload and what they were doing. So this is a quote by one of their leading engineers, and they did a post-mortem for what happened. And what they say is that they were using OpenSearch. They were used to doing queries that were predictive and worked in a certain way. But then one of their engineers sent a CSV file with thousands of requests, and the search requests began timing out. One data node dropped, and then another, and the system completely failed. Okay, so this is just one random example of a system that was built for one kind of interaction, and then when it was loaded, it failed in a bad way. All right. A side note, we're hosting online training events, and our next one is happening next month. It's called Scylla University Live. It's instructor-led. I'm going to be one of the speakers there, and we're doing NoSQL database training sessions. The event is online. It's completely free. And if you want to save your spot, you can simply scan the QR code and just register. Yeah, the event is about 2 or 3 hours. And if you want to dig deeper into NoSQL and database in general, highly recommend it. All right, so agentic AI, this is where we're going. A few more words about what that actually means. So instead of humans being the main users of the database, think about my example from before, me clicking a button. Instead, agents are going to be the ones that are using the database, and they use it in a completely different way. If a human sends requests per second, agents do that per millisecond. Okay, so it's a whole different scale. For humans, we might have a few per organization. We have a predictable number. We can see that in advance. With agents, the number is both unpredictable and unlimited. So even if I do a simple task with Claude code or with Gemini Pro, asking it to do some research task, then under the hood, it might spin, say, 10 or 12 agents, to do things simultaneously, and that can go to even a larger number, and that creates a whole different load on the infrastructure. All right, so I've been talking for quite a while. Let's do a quick poll question just to see that you're with me. So if everyone can please scan this QR code. And the question is, let me change to the poll. How do I do that? Just a second. So please join the Slido using this QR code. You enter your name and email. We're going to do a poll question. And like I said, we're going to use the same system at the very end for doing a short quiz that will have the price of the gift card. All right, so the first question is, let's see that this is working. And the first question is, what database scale do your AI workloads currently require? So is it billions of vectors, petabytes? Are you using high concurrency in production? Are you using a single node or managed databases? Are you using in-memory or POC only, something local? Or maybe you don't have AI needs just yet and you're just here to learn more. So let's give people a few more seconds to answer. Again, if you didn't do so, please take a second to scan this QR code, join Slido, and answer this quick poll question. What database scale do your AI workloads currently require? And like I said, this helps me better understand the audience, make sure you're with me. So I see 2 people answered. Give people a few more seconds if anybody else wants to answer as well. All right, so for the people that answered, the answer is high concurrency in production. So yeah, sounds like you have interesting use cases. All right, going back to the slides. So a few quotes, and I'll talk a bit more about performance, describing the problem. Most AI pipelines work at a prototype POC level, but collapse under production scale. So a question I'm personally asking myself is, where are all those vibe-coded applications that everybody's talking about? So a lot of people are creating applications, vibe coding, but I didn't really see a lot of them out there on the market as the final product. And my personal guess is that yeah, it's easy to get something running at some level, but that last 10% is difficult, and that requires more work, and that's why we're not seeing so many applications out there. Yeah, it reminds me of a quote. It goes something like, it takes 90% of the time to write 90% of the code, and then for the other 10%, it takes another 90% of the time. So yeah, that's been my experience and what I saw from different projects. Another quote is, you can't dig yourself out of tail latency, and that's a super important topic. Let me talk a bit more about that. So what is tail latency? Does anybody know what tail latency is, also called P99 latency? Maybe you can answer in the chat window. So I'm looking at the chat. The question is, what is tail latency or P99 latency? If anybody knows. Right? Anyone have an idea what is tail latency or P99 latency? Give people another few seconds to answer. The question is, what is tail latency or P99 latency? All right. I see that um, either people don't know or they're not answering. Um, it means low latency. That's true, Yasser. And I'll talk a bit more about what it means. So tail latency or P99 latency is an important concept in high performance applications. And what it means is it basically means that the slowest 1% of the latency or queries answered dominates the entire latency. Maybe I'll take a step back and talk about what latency means. So latency is how much time it takes to get an answer for a query. So if I'm sending a request to my database and it takes 1 second to get an answer, then that latency for that query is 1 second. If I send 100 requests to my database and on average the latency is 2 seconds, then that would be the average latency. And what this slide states is that to understand the latency of an application, what really matters is not the average latency, but the P99 or the slowest 1% latency. And why is that? Let me explain. When we interact with an application, whether it's an agent like in this slide or whether it's a human, typically what happens under the hood is what we see here. We click on, say, refresh on our application or website. There are different API calls to the business logic, which are translated into even more database calls. And these can be dozens or even hundreds of database calls. The database provides answers, and this propagates up to the application, and the user gets the page refreshed. Now, because we have for each simple action like a refresh or like a click of a button, we have dozens of database requests. It doesn't matter if the average or most of those queries are answered very fast. The user is only going to get the answer when all those queries are complete. And that is the reason why P99 latency matters. The slowest 1% of the queries or the latency dominates the entire operation. Okay, so here in the slide, I put an AI agent, but just as well it can be a human. Now, I explained what latency is and what is P99 latency, but you might be asking yourself, who cares or why does it matter? And the reason it matters is that typically we're impatient if we are browsing a website, if we're interacting with an application and we have to wait, users become unhappy. We would browse away to another website. We don't have patience to wait. So there are different research, quite a lot of research, that shows that faster interaction for the users creates a better experience. And of course, happy users are more likely to stick around your application. It leads to brand loyalty, and this, of course, leads to higher revenue. So there is research that directly correlates between latency or low latency and higher revenues. I also wanted to say one more thing about latency is that latency is a difficult problem, okay? So basically, database performance is measured in two ways. One is performance throughput, which is how many queries per second we can perform. And the second is latency, which means how fast we get an answer for each query. Now, throughput is considered an easier problem because typically in a distributed database, and I'll talk about that in just a bit, we can simply add more servers or add more memory or more compute to get a higher throughput. So simply we can add hardware, we can basically throw more money at the problem and solve it. With latency, that's not the case. So when users have a high latency, Just adding more hardware doesn't really solve the problem. It's a more complex problem. And it's quite tricky to solve. So different companies are doing different things. I could do a whole talk just about latencies and caching and how to do that, but it's a bit out of scope. All right, so coupled failure loops. What I'm saying in this slide is that there are different points of failure that are coupled together and they add to one another. So specifically talking about AI, if we have high latency, the system's performance is slowed down. If we're talking about AI, we have to constantly keep our data fresh. So we have to continue ingesting data and training our models. We don't want our data to become stale. If the latency is high, the data can become stale and less accurate. Another important thing is contention. So typically with AI systems, we're doing multiple things at once. We might be training on new data as we're also answering queries and answering users, so doing inference, so doing different things within the model. And this whole thing requires quite a lot of training and resources. So if there's a problem in any one of these steps, they add up. And actually, this is this AI generated slide is supposed to be a loop. So it's a spiral. It's not linear, as you see here, because everything feeds into the next problem, and we want to make sure we don't fail in any of these points. All right, so that brings me to specific architecture that is meant to work with AI at scale. I stated the problem. I stated why things are different now that AI is interacting with our database instead of humans. What can be done about it? So that brings me to ScyllaDB. ScyllaDB is a distributed database that's written very close to the hardware with high performance in mind. ScyllaDB has different attributes. I won't go over them, but maybe just briefly. High availability, so it works, as I said, in a distributed manner without a single point of failure. The system is very scalable, so it's easy to add or remove nodes as the system is running, which goes together with elasticity. It's very highly performant, which fits perfectly for AI applications. And I'm talking about the possibility of doing hundreds of thousands or even millions of queries per second at a very low latency. And when I say low latency, I mean single-digit millisecond queries, whereas with some other databases, we might be looking at hundreds of milliseconds per query or entire seconds. Here we're talking about single-digit milliseconds. Price performance, it's easy to auto-tune the system, and the system is compatible with some other databases like Cassandra and DynamoDB. The next part, I'm going to speak about architecture. I'm going to be using ScyllaDB as an example, but what I'm saying is pretty much relevant for other NoSQL distributed wide column databases like Cassandra and Amazon DynamoDB. Scylla is offered either in a database as a service offering, or you can run it on the cloud or on-prem. And let's talk a bit about the architecture and the design decisions. So what we're seeing in this slide is the shard per core architecture. So this is the puppies here on the right. And what we're seeing here on the left-hand side is the thread pool architecture, which is used by some other databases. Okay, so I'm guessing that most of you know what a thread pool is. A thread pool means that whenever there's a task, the operating system selects a thread, the thread locks and performs that operation. Whereas in the shard per core architecture, each core gets its own resources like memory, like networking, like CPU, and it performs in an asynchronous way the work that has to be done. Okay, so the reason that we're seeing the puppies here on the right, you can see that they're happy. Each one has their own bowl of food and they're eating from their own bowl and they're quite happy. No food is spilled and everybody's eating. However, when we're working with a thread pool model, what happens is that we have some puppies eating from the same bowl, some bowls nobody's eating from them. There's food spilled and some puppies are unhappy. If I translate that to databases, it means that the performance is worse. There is contention. There might be a lot of context switching, so it hurts performance. So that's one design decision of ScyllaDB. Another is that it's written in C++. Like I said, everything works asynchronously, and it works very close to the hardware. Let's talk a bit more about distributed architecture. So what we're seeing here is a 5-node cluster. A cluster is a number of nodes working together to provide service. So while we might be thinking of the database as one entity, it can actually be distributed across multiple nodes. A node is a server running the software of the database, and these nodes can be spread in different places around the world, in different data centers, and they all work together to provide service to the user. So distributed systems are complex, and I'll explain how it works. Data is replicated, meaning that it's copied to different nodes. So we keep multiple copies of each piece of data. And that means that there is no single point of failure. Okay? The data is replicated or copied automatically. And as a user, all we have to do is define the replication factor, which means how many copies of the data we're going to hold. So for example, let's look at an example. If here the replication factor as a user, I defined it to be 3, and we have a 5-node cluster. So we have 5 servers, 5 nodes working together to provide service to the user. And I write a piece of data to my database, say this whatever yellow cube is a piece of data. Then that piece of data is going to be replicated to 3 different nodes. And if I write another data, say this cube, it's going to be replicated to 3 other nodes, and so on, and so on. Now, why is this important, or what does this mean? It means that, first of all, any node can provide service. All nodes with this architecture are created equal. Okay, we don't have the concept of leader-follower nodes or master-slave nodes or any other name you want to call it. All nodes are created equal. All nodes can provide service. So that's one thing. And second, and also very important, is that there's no single point of failure. Okay, so because we hold multiple copies of each piece of data, let's say that now node 1 becomes unavailable, there's a hardware failure or some networking issue, or maybe even an earthquake and a data center goes down. These 2 pieces of data would still be copied to some other nodes, and our system would be up and running and remain available. Okay, so here's an example of the ScyllaDB, a database working on multiple data centers. So I mentioned that it's distributed. And here we have an example of a cluster or a database that's distributed around the world, 3 different data centers, say one in the US, one in East Asia somewhere, and one in South Africa. And they're all providing service together. Now, do any of you Sorry. Do any of you have any idea why we would want to use multiple data centers for our applications? What is the motivation to use more than just one data center? If you can answer in the chat window. Just want to make sure you're with me. And again, the question is, what would be our motivation for using multiple data centers for our database? What's the reason to do that? Why don't we just use one machine or one data center? Why do we need more than one? So I see some answers are disaster recovery, avoid losing data, disaster recovery. So that's correct. But there are other reasons. Does anyone have other ideas? Why would we want to use more than one data center? Latency, that's also correct. And there's one more answer that's relevant. Let's see if you can think about it. So legal, availability. Okay, so you got it all. Good job. Let me quickly recap on those 3 points. So one, the first that comes to mind for me is high availability. So if we have multiple data centers, it's spread out geographically, even in the unlikely case that a data center becomes unavailable, because the data is replicated, because we're using multiple data centers, our database would remain up and running and would still be able to work. So that's availability. Second is Alexis mentioned latency, and that's also correct. So it would make way more sense to use the US data center for a user that's sending a query that's physically in the US, right? So if the user is in the US and the user gets the answer from the data center in the US, then that would be way faster than if we would have to serve that user from the East Asia data center. If I remember correctly, just the latency of sending information from the US to East Asia is about 150 milliseconds. Okay, so that's before we even add any compute or any software, just because of simple physics, that would take some time. So that's latency. And the last reason that we see becoming more and more relevant is legal, or you might call it regulations, where some jurisdictions require that data of users remain within a specific jurisdiction. So for example, there might be some regulation or rule that says that we have to keep the data of all our users in Europe within the EU. Okay, so we can simply use a data center in the EU, use multiple data centers for other locations, and make sure that all the data of the EU users remains within that geographical area. This is relevant for every application. It's specifically also relevant for real-time AI. The reason is that this architecture, and I just touched maybe the tip of it, but this architecture supports fast writes. So writes are super fast. It's a bit out of scope for this call, but if you want, you can dig in deeper to understand why. It supports highly concurrent queries, so we don't have to wait, there are no locks. And it's also very easy to scale the database if we need more, to serve more queries. And what do I mean by scaling? When I say scaling, I mean typically scaling horizontally, which means that I can simply add more nodes to my cluster, to my database, as the database is running. So there's no downtime. If I see that the load is high, I can add another node or two. The data would automatically be streamed to those new nodes, and within a matter of minutes, those new nodes will also be answering queries, and that would reduce the load on the entire database. Okay, and I'll show a video of that in just a second. So this is an example from a fire a few years ago in a data center in Europe. I won't use names, but one of our users was using that data center. When that fire happened, there were millions of websites across Europe that stopped working. Our customer, which is a large travel company, experienced no downtime. So they had other data centers that picked up the extra work, and for the users, it was completely transparent. They could continue using the travel application. Okay, a few words about the AI trilemma. So the AI trilemma states that it's similar to the CAP theorem, but different. And it states that we want to achieve three different attributes when we're talking about AI application. One is performance. We want the performance to be as fast as possible. We want the cost to be as low as possible, of course. And we also want the quality of the data to be as high as possible, right? So we want to get accurate answers for our queries. This trilemma states that we need to give a preference to two out of those three attributes. We can't have it all, like in many other things in life. So we have to choose. For example, if we choose performance and cost, then we either get lower quality of results or we don't have high availability. If we give a preference to cost and quality, our performance might be hurt. So we're talking about tail latency that's higher than 100 milliseconds or even more. And like I said before, users are unhappy when that happens. And if we give preference to performance and quality, we might get good answers very fast, but that would cost us typically hardware or networking. And we have some users that are paying just for hardware to AWS hundreds of thousands or even millions of dollars a year. So that's a lot of money. All right, this is a quick example of elasticity. So this is an example. I'll show a video. We have 3 nodes. And what we're seeing here is something called a tablet, which is a unit of storage. And because the load was high, we added, or the system added 2 more nodes as the system was running, no downtime for the user. Let's see it again. And automatically, the system starts streaming those tablets to the new nodes. And even before the data is evenly distributed, those two new nodes can start serving requests. Okay, so it automatically auto balances, and what we saw happens in a matter of minutes. So this is like very, very powerful. Another useful feature with ScyllaDB is something called workload prioritization. Yeah, I won't get into the details, but basically the system allows you to divide your resources according to the workload. So if you have 2 classical workloads, can be real-time data ingestion, and the second workload is typically analytics. So think about an application that, say an IoT application, it measures data from some sensors and writes that data to the database every second. That would be every second sending data, real-time application. Whereas the same application, every once in a while, might say once a day, do a query, reading all that data and performing some big analytics report on that data. Okay, so those 2 workloads have to work together. And when we're doing that heavy report generation, we want to make sure that it doesn't hurt our other workload of continuing to write data to the database, right? Otherwise, the data would be corrupt. So with this feature, we can define how many shares or how many resources we want each workload to have. And by doing that, we can make sure that our OLTP or online transaction processing will continue to have enough resources, and it would continue to work even as we're doing a heavy operation like creating a report. Okay? So this is also very relevant for AI. I mentioned we have contention and contending workloads within the database. All right, let's do another quick poll question. And back to the Slido. For those of you that joined, we're going to be using this platform for poll questions, and we're going to have a quiz with a prize at the very end. So if you didn't do so yet, if you can quickly scan this QR code and join the poll and answer the question. So the question is, which of the following data challenges do you anticipate within the next year? The first option is increased costs, or increased complexity, or slow performance availability issues, or the quality of the data, or maybe you don't know. So let's give people a few more seconds to answer. Again, I'm doing a few poll questions just to make sure you're with me and to see where you're at. And we're going to be using this platform at the end of the talk to do a quick quiz with a prize for the first place, a gift card. So if you didn't do so yet, I see people are still answering. Please scan the QR code and answer the poll question. All right. Let's see if anybody's still answering. Does anyone need another few seconds to answer, or are you ready? All right, let's continue. So I see that for half of those that answered, it's increased costs, and for the other half, it's governance, compliance, and security risks. Those are the challenges. So thanks for answering. And let me go back to the slides. All right. This is an example. I've been talking about performance for quite a bit, but you don't have to take my word for it. We created a quick GitHub example, which you can run on your own. And this demonstrates running a 3-node cluster on AWS with 3 I4I 8x large machines. And what we're seeing here is the monitoring dashboard, and we're simulating a workload running more than 1 million requests per second. You can see that here, and having read and write latencies that are below 1 millisecond. Okay, so this is very fast, and you can play around with it. You can change the workload to be more similar to your use case. And maybe as a side note, if you have a use case that's relevant and you need help understanding if ScyllaDB is a good fit, you can just reach out to me or to somebody from my team, and we'll help you evaluate if it's a good fit. All right, we don't have that much time, just a few minutes. In that time, I would like to go over some use cases and examples from the field, specifically AI applications. So these are some of our users. I would not say that we have a specific industry with most of our users. We have some companies that use ScyllaDB for streaming, some gaming, cybersecurity, ad tech, but many others. And if you're interested in a specific industry, you can simply look on our website and find use cases and blog posts and see what others are doing. All right, so I'll talk in the few minutes we have left. I'll talk about a few AI use cases. One is agentic AI, one is feature store, one is using an AI stack, and the other one is vector similarity search. Let's start with the feature store. So these are some of the companies that use ScyllaDB as a feature store. What is a feature store? A feature store is a type of AI application where we collect features on a specific topic. Features, we can think about them as attributes. So in this example is from ShareChat, which is the largest social network in India, and they're using ScyllaDB to, well, as a feature store. And say there is a user post, you can think about the Facebook post. Each post would have different features, which can be how many likes this post got, how many shares, who is the author, how many comments, and so on. So typically, each piece of data will have dozens or hundreds of attributes, which we call features. And what the system does is it runs some AI algorithms on this data to generate recommendations to the users. And here we see an example from TripAdvisor. TripAdvisor is, maybe some of you know it, it's a travel company. And when a user logs into TripAdvisor, they might ask a question, say, what's the best walking tour in Berlin? Then each user would get recommendations and answers that are tailored to that specific user according to the information the system has about that user. So that information might be their age, previous questions they had, maybe other reviews that they provided, what kind of things they're interested in, and many other pieces of data that would help TripAdvisor give recommendations that are accurate to each specific user. Now, you can imagine that this has to happen very fast. If as a user I'm asking a question to get recommendations and it takes more than a second or two, I would probably not wait around. So this has to be very efficient. I won't go into the architecture, but for those interested, you can find this blog post. ShareChat blogged about how they're doing it. Let me paste that in the chat for those interested. You could just Google it, ShareChat feature store ScyllaDB, and you'll find this blog post. All right, and this is the monitoring dashboard from TripAdvisor. So they're running, in this example, 342,000 queries per second for their feature store, and they're doing it with a P99 write latency of less than 1 millisecond, which is quite amazing, and a P99 read latency of 3 milliseconds. Okay, so it's running very fast, very efficient. I posted this link. This is a side note, two other useful resources for those that want to learn more. I mentioned Scylla University Live, which is our instructor-led training happening next month. And another useful resource is ScyllaDB University. So ScyllaDB University has self-paced courses covering NoSQL, AI, ScyllaDB specific material, and it's completely free. All you have to do is create a user and start learning. So yeah, I highly recommend that. Check that out as well. All right, another use case. So this is from a large electrical car manufacturer that all of you know, but I'm not supposed to say the name of. And they're using, well, those electrical cars have a lot of sensors and they gather a lot of data. And here the use case is to do some model training with that data. They're working at a very large scale. Just to give you an idea, 180 terabytes per node with compressed data, which is a half petabyte per node uncompressed. They're working with tens of nodes, more than 1 million operations per second, and very low latencies. Yeah, I'm not sure if we blogged about this because there is some, yeah, they preferred not to be named, but you can find similar use cases that we did blog about, or yeah, just write me an email and ask if it's interesting to you. Last use case is vector search. Vector search is a more common use case, I would say. And this is the architecture, or how the architecture looks like. So we have ScyllaDB nodes, the database nodes, but we have extra nodes that are decoupled from the database, and they work solely on providing vector search. So vector search, I won't go again into the details, but what it does is it creates something called vector embeddings, and it runs an algorithm to find A and N, or how what's the distance between different pieces of data. And then we can do searches like we're already used to doing with AI, where the system can actually understand the semantic meaning of what we're asking. So it's not like, think about Google regular search, where we ask something and then it looks for similar words like keywords. With vector similarity and semantic search, the system actually understands what we're asking. And ScyllaDB supports vector search. There's a specific query language to do that. Again, I won't go into the detail, it's a bit out of scope, but great results as well. All right, so to summarize before we go on to the quiz, what actually matters at scale is that our data remains fresh and up to date, that we have a consistent P99 or tail latency, that our resources are isolated and we don't have contention, so we can prioritize different workloads, and maybe last but not least, cost predictability. This is especially relevant. Some databases, like we see a lot of users migrating from AWS DynamoDB. And with DynamoDB, it's a popular database. It works well, but the cost is very unpredictable, just because the way they price their usage by operation and networking, and it can run out of hand. It's really hard to understand the cost with DynamoDB. And we're seeing users migrating from DynamoDB to ScyllaDB and cutting their costs by 50%, which can be a lot of money. So things you need to do, I'll skip that. And let's skip to the quiz, because we're almost out of time. So we're going to do a quick quiz, and like I said, the winner is going to get a $50 Amazon gift card. Let me jump forward to the quiz. All right, so please join the quiz. We're going to have 4 questions. For the quiz, to join, you can simply scan this QR code, enter your name and email. It's going to be 4 questions, not very hard. And then we're going to have a leaderboard, and the first place is going to receive that gift card. Awesome. And by the way, you get your score according to how fast you answer the question, and of course, getting the correct answer. So the scores again are by how fast you answer and getting the correct answer. I see that Alexis just joined. Maybe Alexis, you want to join the quiz as well? We're doing 4 questions with a gift card for the first place. So I see 2 people joined. Let's wait a second and see if more people want to join. And giving people another second. Meanwhile, I'll answer the question. So there was a question about DynamoDB versus ScyllaDB. Sorry. I'm copying it into the chat window. And then we will start with a quiz. So if you want to look at DynamoDB compared to ScyllaDB, you can look at this page. And let's start with a quiz. Hope you're ready. So the first question is, the replication factor, or RF, determines the number of clusters that will be replicated, how many copies of the data exist, the number of nodes in the hash ring, or the minimal number of coordinator nodes. Which one is it? What does the replication factor determine? And the correct answer is how many copies of the data exist. So half of you got it correct. Next, what AI attributes break databases? Is it huge scale, enormous bursts, irresponsible vibe coding, or all of the above? So I talked about this at the beginning of the talk. How can we break databases with AI? And most of you got it correct. The correct answer is all of the above. Lots of things break databases. All right, next question. ScyllaDB achieves high availability by having all the communication between nodes peer-to-peer, replicating data, having no single point of failure, using multiple data centers, or maybe it's all of the above. How does ScyllaDB achieve high availability? And again, most of you got it correctly. All of the answers are correct. And last question. A cluster is a collection of nodes, rows, columns, tables, or partition keys. What is a cluster? And this one is apparently easy. So all of you got it correct. It's a collection of nodes. And let's see the leaderboard. So Vered got it correct. Good job, Vered. Let me make a screenshot of this. And Alexis at number 2, then Yasser, then Edward. And again, sorry if I'm mispronouncing names. Good job, everyone. So let me go back to the slides to summarize. Another event I want to invite you to is called the P99 conference. So P99 latency is so important that we created an entire conference just about that. It deals with high performance applications in general. It has really interesting talks. It's online and completely free. And you can save your spot at p99conf.io. So make sure you do that. And I also created this QR code with a gift of, you can choose one of the 4 books in a PDF format, so it's completely free. One is ScyllaDB in Action, one is Database Performance at Scale, one is Designing Data-Intensive Applications by O'Reilly, and the other one focuses on latency, so just an entire book on latency. Oh, you're not seeing the QR code. Sorry about that. Now it's working? Okay, thanks for letting me know. So I'll give you another few seconds to scan the QR code. And yeah, let me also write my email in the chat window. So it's very simple. It's guy@scylladb.com. If you missed the QR code, or you have a question, or you just want to say hi, write me an email. So thank you for joining today. I hope you learned something. And stay in touch. You can say hello on the community forum. That's forum@scylladb.com, or just shoot me an email.